Hey everybody, I wanted to give you a little bit of a summary for what we did in physics today. So we started off with a couple definitions. We defined distance, displacement, speed, and velocity. And we talked about this notion of a vector versus a scalar. And if you remember, a scalar is just a number. And a vector is also a number, but it has a direction. And just in this unit, we're really specifying the direction by saying positive is forward and negative is backwards. And we define the distance as the total amount that you cover. Displacement is your final minus your initial position. Speed's how fast you go, and velocity is speed and a direction. And of course, we're going to get to a little bit of this. We talked a little bit about it with the notes that we worked out today. But for example, if I start on a meter stick and I say I go from 0 to 1 meter, and then I go back to 0, my distance would be 2 meters, and my displacement would be x final minus x initial. I entered at 0, starting from 0, so my displacement is 0 meters, and that's kind of the difference. And then, of course, we had speed, which is how fast, which is your distance over your time, and your velocity, which is your displacement over time, as a quick definition. Now, the real focus, though, to get us into motion was I gave you a quick little mini lab with the buggies where you graphed position versus time. And then I asked you to plot the velocity versus time, which seemed a little weird at first. Because everybody, I recall, we wanted to do this for our graph, and we realized that was incorrect. What we realized is that we get a steady slope, and therefore, for plotting that velocity versus time, it's a steady slope graph the whole time. We came up with a conclusion, which is that for x versus t graphs, we came up with a couple things. The y-intercept is your initial position. The slope is your velocity. Positive slope meant forward, right? Negative slope meant backwards. And the displacement was given by, say, if I start here and here, or I end here and I start here, just plain old x final minus x initial, and it's a nice subtraction. When we do v versus t graphs, though, a couple things popped up. First, we realized the area is the displacement. So we actually take the area of this rectangle here, and that actually gives us the displacement of the object as well. That was the key finding, and that was kind of the launching point for the rest of the physics that we did today. Now, what did we do with this physics? If you remember, we took this idea of v versus t, and here's what we concluded. We said, hey, if I graph it like this, if this is v naught and this is some v final, the key idea is the area of a v versus t graph gives us the displacement. So we have the graphical interpretation, which is that for a nice graph like this, we could say the displacement is the area of the trapezoid, right? So we can do a complicated calculation like that using the area. But then that's one thing that we did. That's kind of the graph part of the physics that we did today. But then we went ahead and we did what I'm going to call an equation part. We realized that v here is at plus v naught, okay? And then we did a lot of algebra. And what did we conclude? We concluded that there are actually 3 equations that we can use to describe the motion of an object. One is we get its position as a function of time. Then we get its velocity as a function of time. And then I didn't prove this, and I'm not going to make you prove it, but if you isolate t here, plug it into here, you can simplify after a lot of algebra, and you obtain the following formula that is useful when time isn't given. So we today worked on 2 things, using graphs to get displacements, and the other thing that we did was we used this graph to come up with three equations that we used for problems. And one small thing I want to point out is when you've got a velocity graph, remember that the slope is the acceleration, which is your rate of speeding up and slowing down. The other thing that we did is we got really careful about labeling all our letters, right? So let's just review that now. These are easy. This is time. This is acceleration. This is your position. This is your initial position, which means your starting point. We had v as velocity. And v naught is your initial velocity, which is like your starting speed in the direction that you're going in as well. So that's really what we worked on today. Again, just the logical sort of progression of today. We did a lab with the buggy where I had you plot velocity versus time, and you came up with a boring graph. But what we realized is the area under this graph tells us the displacement, which is the amount that you cover. From there, we took this idea of area under the V graph and went in two directions with it. One is we realized if I want to get displacement graphically for an accelerating object, I can still use the area. In this case, it's a trapezoid, sometimes it's a triangle. But then we went in a second direction, and we actually derived equations, what we call the equations of motion for an object accelerating at a steady rate. These are these three equations here that would always give you on quizzes and exams. So that's a pretty decent summary in 4 or 5 minutes of what it is that we did today in day 1 of Accelerated Summer Physics.